In this lecture, I'm going to show you how to derive the Nernst equation and put it to some test using a demonstration. So in any case, let's get started. We know that the Nernst equation is nothing more than an equation that will tie in our delta G, or Gibbs free energy, that measures spontaneity or direction of a reaction, with net potentials, okay? E of cells, sometimes people call them. And we know how to get these from standard conditions. We get delta G from tablature a lot of times using delta H minus T delta S. And we know we get the net potentials, the overall voltage for a reaction, by looking at tablature of standard reduction potentials. And using the voltages, we add them together, flipping, let's say, the oxidation half reaction, and we get that voltage. Now, they're tied together. We know that redox reactions, if they go forward, okay, produce a voltage. A positive volts, we've always said at this point, means spontaneous. Now, spontaneous means the redox reaction goes forward. Now, positive volts really mean that the element that is being oxidized and the element being reduced are compatible for each other in the sense that they will, in a sense, pass electrons around. Someone's a good enough oxidizer, someone's a good enough reducer to have an exchange of electrons to push the volts around a circuit, so to speak. Where voltage is joules per charge, or coulombs. So it's the energy per charge. It's kind of like the energy that pushes the charge around, let's say, a circuit or a DC circuit. And it's all tied to, let's say in a battery, of the chemical that gets oxidized, that pushes the electron, to the chemical that accepts them. Now, the one that pushes them is the one who gets oxidized, or the reducer, and we call that usually the anode, and the one who accepts is the one who's getting reduced, and that's the oxidizer. And essentially, that's what's happening. Electrons can be passed around, and that can, or the ability to do so, is what the voltage measures. It's potential difference in charge. Okay, it's not necessary. It's not the electrons being passed around. It's the pathway is there. Now, in any case, getting back to all of this, all right, we have this reaction, and through other derivations and experimental evidence, mainly through diluting solutions, we've learned that when you dilute a solution, let's say you go from 1 molar to 2 molar, we notice the entropy, okay, decreases. So as you add more water for the same moles of solute, the disorder decreases because there's less of them. Okay, now of course I went from 1 molar to 2 molar. That's not dilution. I should have said 2 molar to 1 molar. Sorry. And so from the experimental evidence, we've learned that delta G, okay, non-standard, is equal to delta G standard from tablature plus RT ln of Q. All right, and that's something we've already dealt with before, and it's something that we derived by using the experimental evidence of dilutions and combining it with our current understanding of Gibbs free energy, this formula. So we've got this formula. Now we know that Q is the reaction quotient, it's products over reactants, and it's the value of the concentrations of the reactants and products when you're not at equilibrium. But when you are at equilibrium, okay, let's go even further. So at equilibrium, this becomes K, but we know that delta G at equilibrium becomes 0. So 0 equals delta G, okay, standard conditions, plus RT ln of Q. And now, of course, that's ln of Q anymore, because at equilibrium, it's ln of K, or KEQ. Now we're going to solve for delta G. And so delta G is equal to negative RT ln of K, which is the equilibrium constant. And that was the formula we used to notice that if the K is high, which means you have more products than reactants, because K is the concentration of products over reactants, okay, then you have a highly negative delta G, which makes sense. If you have a reaction that favors products, the reactions are going to go toward the products, and you're going to have a reaction that is spontaneously in the forward direction. Remember, delta G measures direction, pathway. So if A plus B makes C, and we know at equilibrium there's a heck of a lot of C, then the reaction loves to go forward, and delta G is very negative, okay, at the forward direction, which means it has this direction. Delta G measures directionality. Now, with things that are redox reactions, if they go spontaneously forward, they produce a voltage, a positive volts. They produce that scenario where they can push charge around. Voltage is a pathway for electrons to go. So if redox reactions are spontaneous and they go in one direction, then how can these positive volts that people have told people, how does that mean negative delta G? Well, we tie this together by saying delta G is equal to the net potential by adding the reduction potential and flipping the reduction potential for the oxidizer, flipping that sign, adding them together, and you get E0 of cell. So you get those volts. And what this is voltage, and now voltage, by the way, is joules per coulombs, and then you're going to times this net potential by Faraday's constant. This is a fancy F. The Faraday's constant 9.6, said 6 but I wrote 5, 9.6500, and these are coulombs per mole. So Faraday's constant is a converting factor that tells me how much charge a mole of electrons has. So here in this way I'm converting my joules to mole, because delta G, my friends, if you remembered, is in kilojoules usually per mole. So delta G has to be in some energy unit, so we're going to get real coulombs. So we're going from joule per charge, figuring out how much charge we have, we can figure out total amount of joules. Now this little n here that I'm going to put is not necessarily moles, it's really a ratio of how many electrons per reactant is being transferred to make that happen. For instance, if you've got aluminum plus 3 going to aluminum, it's going to gain 3 electrons to make aluminum 0, the solid aluminum. This of course is reduction. We would say that if this was 3 electrons in the reduction half reaction, and there was 3 electrons being passed around or produced in the oxidation half reaction, this number would be 3. Is it 3 moles of electrons? Well, it's a ratio of 3 moles of electrons per 1 mole, let's say, of aluminum plus 3. So we have to look at half reactions to do that, but you have to look at balanced half reactions, not just halfway. All right, so that N would equal the ratio of electrons involved in both sides of a half reaction that get canceled. So that's a dimensionless unit because it's moles of electrons to moles of the reactant, or the oxidizer, or the reducer, however you want to look at it. And because it's moles over moles, it's dimensionless. So this would be some number, okay, integer 1 through whatever. If you notice, coulombs cancel, you're left with joules per mole, which is a unit of delta G. However, wait a minute, positive volts would give me positive delta G. That's not going to work. So we've got to put a negative sign here. So our new formula that connects net potentials or electrochemical cells is take your volts that you get from your tablature, times it by Faraday's constant, okay, and times it by the negative, times it by the ratio of electrons per particle in any case, and you put a negative in front, and that's how we convert positive volts into negative delta G's, if in fact this is positive, right? Because as you've learned, some redox reactions are not positive, they're negative, which means you have to add energy to make them go. Okay, remember, positive volts mean really positive joules, the energy that's being pushed around. This is negative energy. So in electrolytic cells, like electroplating, okay, or electrolysis, you have to add energy to force something that's non-spontaneous. So negative volts would show a non-spontaneous process. You know, if it's a negative times a negative, this would make it positive, and positive delta G, of course, is non-spontaneous. So it's important that you realize that this number generated here really starts and ends with the voltages you get from your net potentials. Okay, but we're not there yet because I still need one more equation. Now, some people can look at this and say, well, there's one more equation to this before we get started, so we can do that. I can set this negative NFE, negative F, fancy F, and I'll start again. So I can do delta G is equal to N, is my fancy F, and then, of course, E of cell, and that's equal to delta G from delta G naught, which is from tablature, standard conditions. And I also know that delta G naught is equal to negative RT ln of K. And I noticed my mistake up here. This should have been a not symbol. okay? Because if I don't have that, that's non-standard conditions. So if I set these equal to each other, all right, negative NF E0 cell equals negative RT ln of K, what I get is, well, I'm going to divide by negative NFE, negative NF, negative NF, and what I get is E0 of cell, which is the tablature voltages, equals RT over N, fancy F, Faraday's constant, ln of K. Now what does this mean? Well, this is a nice little formula to look at something. If the K is high, if your KQ is high, which means there's a heck of a lot more products than reactants at equilibrium, then your voltages will be positive, because the natural log of a positive number is still positive. I'm sorry, natural log of a number greater than 1 will be a positive number. If your reactants are larger than your products, so what's going to happen is you're going to have a natural log that becomes negative, right? Bigger, a number smaller than 1, put it to an exponent, becomes a negative value, and now your E of cell becomes negative. So if you've got a lot of if you have a high K, that means you have products are favored, and in my half reactions, reactants become products. If I got a lot of products favored equilibrium, that means we have a directionality to go forward, which means we're going to have positive volts. Okay, so that kind of shows you that. All right, so let's continue on. The last and final derivation, of course, is the Nernst equation. And we'll look at that from the perspective of delta G equals negative NFE. And what we're going to do is, we know that delta G non-standard, this is standard, must be equal to negative NF non-standard E of 0. So what we did here is we created another equation where we have the non-standard E, although I wrote it, okay, equal to the non-standard G. And what I'm going to do with these two, I'm going to plug these in, which represent the non-standard G and the standard G, and I plug them into this equation up here, right here. Okay, so let's just clean this up a little bit to see what I am talking about. All right, so again, I'm going to have delta G standard conditions or not, okay, so delta G naught, which means from standard conditions, equals negative N, fancy F, okay, to E0 of cell, net potentials. Also I have delta G non-standard equals negative N, Faraday's constant, okay, non-standard cell. A lot of bells. Okay, now I also have the delta G that's linked to the ln of Q, which is delta G, okay, equals delta G naught, standard conditions, plus RT, natural log of Q, your reaction quotient. So now what I'm going to do is I'm going to now just simply plug in the values for the non-standard and the standard here. So what that gives me is negative NF E of cell, non-standard, equals, now my standard, negative NF E0 of cell, plus RT ln of Q. All right, now we're going to now solve for non-standard E of cell. That's what this is about. We're trying to find an equation that we can figure out, hey, it's great that we can get net potentials from tablature, but those conditions have to be 1 molar for each solution and 1 atmosphere for the pressure at a certain temperature. That's great, but I'm never usually at standard conditions. So we solve for E of cell by dividing by negative F, Faraday's constant, all the way through, negative NF and negative NF. Okay, well, you can see that this will cancel. What we get is E of cell, without this little degree sign that means non-standard conditions is what we like, is equal to negatives cancel, NF cancel. What we get from tablature okay, minus that negative sign takes over, RT, of course this R is going to be in joules, okay, it's 0.031 or something, 0.8, whatever, negative, oh, negative's gone, the 0.8 value, yeah, is N of F there, ln, natural log, if I can write it, I'm not sure what I just did there, natural log of Q, which is a reaction quotient, which is products over reactants, coefficients become exponents, and solids and liquids don't apply. So let's get rid of Q so we can understand this a little better. Q is going to equal, okay, is going to equal the product concentration over the reactant concentration. All right, let's see if we can make some sense of what the Nernst equation really can help me do. All right, so let's build a Daniell cell. Okay, let's take some zinc in a beaker. And this would be my zinc electrode. And let's make another beaker and put in copper. We're going to have a solution of each. And here we're going to have, let's say, a 1 molar solution of zinc nitrate, which is really a 1 molar solution of zinc ions. This is a 1 molar solution of copper 2 nitrate, which is really a solution of copper plus 2 ions. Okay, so I've got zinc plus 2, and I have copper plus 2 in here. We know that we'll connect these electrodes by an external conductor or wire. And let's review a little bit between zinc and copper. Who is better at oxidizing? Well, if you look at the standard reduction potentials, I'm going to write them. Let's go find them. So this is a standard reduction potential table, and we're going to look for our copper and our zinc. So copper, okay, becoming copper plus 2. So here is the 1 net reduction potential for copper plus 2. And they look at zinc. Zinc is down here. Now, how do I evaluate this? Well, very simple. The more negative, so if you think about it this way, we're looking for who's going to oxidize better. Since this is a reduction table, meaning we're gaining electrons, or charge is going down, metals don't like to gain electrons. So they're going to be a negative. So ions of metals, okay, should have negative reduction potentials to show that it doesn't happen very well, which means that the forward reaction really works. As we talked about before, a negative net potential means it's non-spontaneous in the forward, but really spontaneous in the reverse. So that means that metals with these negative numbers all would flip these arrows around. These all want to go this way. The negative voltages is telling me, hey, that way is the way we like to go. So if you think about it, the zinc, its oxidation potential is positive 0.76. All right, just changing the sign going that way, because positive volts times NF what? E of 0 gives you negative delta G, which means spontaneous, which is a direction. So who likes to go to the left the best? Who would be the positive volts? Well, look at copper. Copper going this way would be evaluated as negative 0.34. So it doesn't like to oxidize. So the metals in this table with the greater negative reduction potentials really tell me that they have greater positive oxidation potentials. So zinc is better at oxidizing. Think of the most reactive metals you know. Dropping what? Sodium in water, explosive. Rubidium in water is, cesium in water is explosive. These guys love to oxidize. So in any case, your activity series show increases as you go down, or the ability for the metals to lose electrons or oxidize. So zinc is better. So we have a 0.76 for zinc oxidizing, and we have this copper here. So from doing that, I know that copper or zinc is the anode. How do I know? Anox, red cat, and red cat means reduction occurs at the cathode. So this is the anode. It's place of oxidation. It's better at oxidizing. So what does it do? The zinc 0 solid metal becomes zinc plus 2 by losing 2 electrons. That's oxidation. Leo the line, losing electrons. Electrons in the product side. Then what happens over here? Well, copper doesn't like to oxidize, but as we can see in our table, copper plus 2 likes to do what? Likes to go in the reverse, right? It's positive 0.34. Copper plus 2 loves to go this way. Why? Because it's positive volts. Okay, it's spontaneous. So copper plus 2 becomes pure copper. And if you haven't recognized this, it plates on here. So this becomes pure copper right here. So copper plus 2 gains 2 electrons that supposedly are being conducted through the wire onto this plate, and it becomes copper 0. Okay? Now, the overall reaction in this process is what? Well, copper plus 2 plus zinc gives me zinc plus 2 plus copper. Notice the 2 electrons cancel. If I wanted the delta G of the reaction, that'll be my 2. See the 2 electrons here? So delta G would be equal to the 2 Faraday's constant, which is 9,560, I believe. So 9650 coulombs per mole times the voltages. Now voltage is, voltage is a joule per coulomb. And where do we get the voltages from? Well, how do we know that the E0 cell here? Well, easy. Let's go find this reduction potential. Bring up my chart again. And there it is in all of its glory. And we get a reduction of 0.34 for the copper. So 0.34 volts. And for the zinc oxidizing, okay, I wouldn't put a negative because it's oxidizing, it's going reverse, it's positive 0.76. Okay? And this is positive 0.76 because I'm doing the oxidation. Add that together and you get 1.10 volts. This is equal to my E0 of cell. This is the standard potential or potential difference of charge I should produce. It's a pathway that basically depends upon the ability of copper plus 2 to absorb electrons and zinc plus 0 to push them. So zinc plus 2 is pushing electrons and copper is sort of pulling them through. And that difference, that potential difference, is the energy that pushes charge around. Doesn't mean there's electrons flowing. Okay, so I'd put this 1.1 voltage in here, 1.10, and notice the coulombs cancel, joules per mole. This number of 2 I got from the balanced electrons, the ratio of electrons per reducer or electrons per oxidizer, and I times that through, and that's what I come up with my delta G. In this case, of course, it come out joules per mole, and you can convert to kilojoules, and that's how you'd use that. But that's not the Nernst equation. That's not what I'm really after. What I'm really after is, what if I don't have 1 mole? What if I have changing concentrations? So let's look at the Nernst equation again. Okay? Now, back with the Nernst equation, which is a way to see how we get what? Non-standard. Now, this is standard from tablature. Watch what I do here. The products over the reactants. Now, if I look at my overall reactant, okay, we see that zinc 0 is a solid, copper 0 is a solid. So the only reactants and products that I can put in here is copper plus 2 aqueous and zinc plus 2. Notice zinc plus 2 is a what? Product. So back to my Nernst equation, zinc plus 2, and that's a concentration, over my copper plus 2. Copper plus 2 is a what? Is a reactant, where zinc plus 2, is a product. So, interesting enough, all I have to do is play with these concentrations to mess around with my current conditions, or my what? Conditions that are perfect for 1 molar. For instance, if I was to dilute and add water, if I was to dilute the concentration of copper, so if I added water to this and dilute the concentration, okay, I could change it. Now, I noticed something, and people probably, the purists out there are screaming to me. I haven't added a salt bridge. Okay, a salt bridge would allow electrical neutrality to be had, because over time, if you notice, zinc plus 2 is going to get produced. So zinc plus 2 is going to get positive. This beaker is going to get positive. We label the anode by convention negative in battery or voltaic cells. We label the cathode positive by convention, so to show that charge is going from negative to positive. But as solid copper becomes zinc plus 2, this beaker is going to become positive. If the beaker becomes positive, electrons are not going to go away from a positive. So we have to have something in a salt bridge like, I don't know, negative ions from a salt to move down to counterbalance the increase of positive charge. Over here, we're losing copper plus 2 as it gets reduced into pure copper. So we're losing copper plus 2. So the positive ion in the salt bridge moves down to what? Counterbalance the loss of Cu plus 2. Also, the nitrate ions are negative, and they could go through here and also counterbalance the positive 2 here. So it allows ions to flow. It keeps this beaker, both beakers, electrically neutral so the charge can flow. So back to where I wanted to talk about. Now, I'm going to change the copper. So what I'm going to do is I'm going to decrease the concentration of the copper plus 2. And when I do that, what's going to happen? Well, this Lin value is going to get smaller. Okay? In fact, if I lower this number, it gets bigger, right? If I lower the denominator, okay, if I make this number a smaller number in the denominator, this makes this number larger. Okay, so if I change the concentration of my denominator and I make it smaller, it makes the whole expression here a bigger number. Notice this negative value here. So what happens is I'm going to make a larger negative value. By making this a bigger number, this whole expression, this becomes a bigger negative. And then when I subtract a bigger negative from E0 of cell, you can see that my voltage, which should be 1.10 volts if I had 1 molar of each of these at 25 degrees Celsius, those are the what? E0 cell conditions, is only going to go down to something lower if I lower the concentration of the copper ions. Now why does that occur? Look carefully, it's the Chatelier's principle. If I lower the copper concentration, copper plus 2 ion concentration, this reaction will shift to make more. And I see there's a problem here. This should be pure copper. Okay, sorry. Do that one more time. So this should be pure copper. I'm not sure why. Someone should have told me while I did that. Right? Copper is the overall reaction here. It's a solid metal. So if I lower the copper concentration, the reaction is going to shift to make more. So the reaction is going to go in the reverse. If we're going in the reverse, that means the forward reaction can't be as spontaneous, and delta G becomes positive for the forward. And positive delta G for the forward means negative volts, okay, or it goes down. Now, you can look at it another way. If I lower this what? Cu, okay, my what? Well, if you think about K is, well, we know that we just changed our Q, right? And by changing the value of Cu plus, by lowering it, okay, now you have less reactance than you're supposed to have. Having less reactance means that your Q is greater, let's say, than your K, and the reaction moves in the reverse. And so the reverse reaction is spontaneous. And this is the kiss of death for redox reactions. Redox reactions do not want equilibrium. They do not want a competing reaction to go the opposite direction. We want to go one way. So to lower the voltage, okay, you could do that. Now, that happens naturally, right? Because over time, what is going to happen? Over time, you are going to lose your copper. So over time, your copper is going to go down, okay? And that's why your battery's dying. One of the reasons. You're going to run out of copper plus 2 ions, okay? Now I can do this another way, right? I could, let's take this stuff out of the way. I could what? Increase the concentration of zinc plus 2. Now if I increase the zinc plus 2 concentration, think with me for a second, this becomes a bigger negative as well. Look what we're doing down here, people. You increase the zinc concentration, okay, I'm sorry, I keep doing this incorrectly. It's the zinc plus 2. I only can mess with these guys. So if I increase the zinc plus 2 concentration, the reaction shifts to lower it. Le Chatelier's principle. And guess what? We're going opposite of what we want. So the E0 cell also will drop. Okay? So what if I want to increase the E0 cell? Well, I got to either do what? Decrease my zinc concentration. By decreasing this number, ln, of a number less than 1 becomes negative, right? And that becomes positive. So if I decrease my zinc plus 2 concentration, or I increase my copper plus 2, either one is going to make my ln of some number less than 1. Anything less than 1 for an exponent, that's a natural log here, is a negative number. And this negative number plus this is a positive. So if I decrease zinc plus 2, let's get this stuff out of the way. Think with me for a second. It's Le Chatelier's, I decrease this, the reaction wants to what? Go forward to replace it. Or if I do what? Increase copper plus 2. Notice that's the what? Same thing above here. That will what? Drive the reaction forward more. The reaction will be shifted forward more, and we would get something above 1.0. So I need to increase the concentration of copper plus 2 and decrease the concentration of my zinc, and I can force greater volts. And that, my friends, is how the Nernst equation explains how the voltages vary over time. But it can explain something far more impressive. All right? The Nernst equation, because it's what? Essentially messes with what? The ratio of ions of products and reactants. Here's what I also can do. I can build a cell completely of, let's say, zinc. This is zinc, and this is zinc. You say 2 electrodes of zinc? Absolutely. And I have zinc plus 2 in both of them. And you may say, how is that going to work? Shouldn't one be another compound that'll give me positive volts? Well, watch. I can change the conditions. So let's make this zinc 1 and zinc 2. This is zinc 1. This is 2. And make this 2 blue. So zinc 2 is blue. Zinc plus 2, 2. So let's pretend I've got the red zinc 1. All right. And what am I going to do here? Let's pretend it oxidizes into zinc plus 2 and 2 electrons. Right? Then we have what? Zinc plus 2 over here could gain 2 electrons to become zinc 0. That's what this is. Or zinc 2, however you want to think about it. Okay? Now, you would say the net potential here should be 0, and you're absolutely right. This would be a positive 0.76, and this would be a negative 0.76. So you get an E of 0 of cell to be 0. Well, let's go back to our Nernst equation. If this goes to a 0, then all I'm left with is the rest of this. Hey, so I can't have equal concentrations. The ln of 1 is 0, and all of this becomes 0, E is 0 cell, right? So if I have equal concentration, if I had 1 molar and 1 molar, it's not going to work. What concentration will work? Well, think with me for a second. We have zinc plus 2 is a reactant, so that goes in the bottom. So we have, where is it? Okay, zinc plus 2 is a reactant, so let's get this out of the way. So we have zinc plus 2 blue is a reactant. I keep saying it. And then I have red zinc plus 2. Make sure I do that correctly. Red zinc plus 2 is a product. Yeah, okay, I did that correct. Now watch, party people. In order for this E0 cell not to be 0, to produce, guess what, a voltage, just by changing these concentrations of the same thing, what do I need? I need this expression to go positive. How do I do that? Well, I need this natural log to become a negative value, an exponent. I need something smaller than 0. So I need a small amount of this and a large amount of that, right? If I make this smaller than the blue, this becomes what? Less than 1, and a log of something less than 1 becomes a what? A negative expression. So if somehow I have a smaller concentration of zinc plus 2, right, and a higher concentration of this zinc plus 2 blue, that would cause my reaction to go forward, right? Greater number of reactants, and I lower the products, I'm going to shift the reaction forward, Le Chatelier's principle. And depending upon what this reaction is, how lower would give you some voltage. My friends in chemistry, that is how cells produce a voltage. That is how axons produce a cell potential. That is how your heart produces its own pulse. Okay, our whole nervous system depends upon this equation. Now, we don't have zinc changing. It's potassium, sodium, potassium, a sodium-potassium pump that changes the concentration of these through semi-permeable membranes and a phospholipid layer that allows the concentrations of the K and Na to change, and that's what creates a potential. If you lower one of them and increase the other, you'll create a potential, and that's the electricity that flows through our body. All right? So pretty important equation of life, I believe. All right, hope that helped.